Cool. Okay. Hello, guys. Welcome. Welcome back to Live Maths with me, Paul Tutors Maths. You've had a break for the weekend. I hope you're recharged. I hope you're ready to go. Yeah, as usual, just the usual stuff, really. Usual chat. Subscribe to this channel. Feel free to like the video. That does help things. If you're enjoying what's going on here, I'm just trying to get through nice exam questions, AS level, A level. Keep you guys sharp out there, keep you fresh, and keep going with the maths. Mechanics, it's been neglected. We're remedying that today. It's just one question. It's an AS level question, but it's a harder AS level question. I didn't want to scare you off too strongly, although there is a lot of words in chat. But yeah, let's go for that. Anything else to say? Probably not much. Only thing to say is the actual YouTube content, that is coming. As in, not live stuff, non-live. We're going to have some maybe non-live maths. It's coming at some point. It's not here yet. Watch this space. Chit chat finished. Mechanics and pulleys beginning. I'm going to draw the thing kind of quickly. Let's see. Seems to be a little bit of a delay on the thing, is it maybe? Well, technical issues. Well, I'm just going to go with it. Let's see if it catches up with itself. So, right, okay, doing that around the pulley and coming down. Okay, so I've just drawn the thing basically. I've not done anything much more crazy. Yeah, it does seem to be a slight delay on the video for some reason. We'll survive. Now, it's got a lot of chat, all right? There's a lot of wording, short story there. Ultimately, the question says write down the equation of motion for A. So I'm going to actually start there and we can work back as we need to. A. That guy at the top, and to get the equation of motion we need the forces. So I'm going to draw some forces on A, and then I'll explain what they all are. Okay, so 4 arrows, up, down, left, right. This is how you always have to do it. It's always going to be a story of F equals ma. That's Newton's second law. That's something that says the acceleration times the mass gives you the resultant force. And in there it's forces we're looking at, and therefore we need arrows to make forces. Here you've got the tension, which is going along the string. That's the thing that's pulling A to the right, because maybe I should just explain what's happening here. These two things are being put in place. Someone's holding them, then they let go. And when they let go, B is going to fall down, and A is going to move to the right along that slope. You got that? So hold these two balls, let go of them. Since B is heavy and kind of dangling, it's going to pull that down and bring A along with it. So that T is the pullage. It's how much B is pulling A along. That's that force. It's called the tension. It's the tension in the string. Fr is friction. That's pushing back the way. And here they've actually said, if you read the question, it's 12.7 newtons that's pushing back the way. Depends on the question. Depends what if the slope is rough or smooth. But this one they've said it's rough. when I say rough or smooth, bit of weird language. You know, is it like an ice rink, or is it like some sort of jaggedy piece of wood? If it's an ice rink, there'll not be any friction. If it's a jaggedy wood, there will be. Here there is. So, lots of chat. Always get too distracted, especially start of the week. I'm excited about the maths. I shouldn't be doing that. I should be writing out the formula, and here it is. We're going to call this direction positive. That's clockwise. And then, so Newton's law that F equals ma on A, as in ball A, not A acceleration, is going to look like this. T, that's the force to the right, minus 12.7 equals ma. So, anything else to say about that? Yeah, that 12.7 is the friction. That's the arrow going back the way. T is the arrow going forwards, and they're going to equal ma. Let's plug in what I can. T minus 12. I mean, I already plugged in the 12.7. The other thing I can plug in is the mass, which is 2.5. Let's just check that in the question. Yeah, looks good. So actually, that's the answer to 1. Let's keep going and get 2, and then I'll do a recap of it. 2 wants you to do the same thing for B. So actually, quite liking this delay, quite enjoying this delay to the video feed. It gives you a chance to do it. It gives you a chance with your pen and paper to think, can I actually do this question? Sit down and bust it out. I don't want you relaxing. I want you focused and engaged. So here we go. With B, what can we do? What are the forces acting on B? So you've got the weight down the way, and you've got tension up the way. And that is the only two. It's not resting against a surface. So all it is dangling there. It's got gravity pulling it down, and it's got tension coming back up the rope. That's one thing to note, that you've got tension coming up the rope and a tension pulling the other thing, and they should be equal. And watch how the arrows go. Anyway, enough talk. So taking that taking the clockwise direction as positive, W minus T equals ma. Maybe I'll even just write in something like, I know it's a bit confusing because there's two A's. They've called the actual ball A and there's A for acceleration, but these are the, this is to do with ball A and this is now to do with ball B. W minus T equals ma. This W minus T is F. It is the F of F equals ma. F is like unbalanced force. That's really what F means. You'll often hear force is ma, or force is mass times acceleration. But just saying it force is a bit, it's not really giving it credit. It really means the unbalanced force, the net force, the resultant force. It's like adding them all up, and then whatever they all add up to will equal ma. So here you go. Two forces, W and T. What can we plug in? Well, T we don't know. Mass is 1.5. And the weight here, well, how many of you guys have taken your qualifications for conversion of mass into weight? Because you will need that permit ready to go. And if you've done GCSE physics, you'll be all over this. If not, you might need a little bit of a push. But that's it, just so you remember. Weight is the mass times g, which is the gravitational constant. And here we're saying g is 9.8. Okay, so the mass of this guy is 1.5, and we can times that by 9.8, I guess. It could be 1.5 g, or you could times it by 9.8. Let's times it by 9.8. Write it out, and then I'll just do a recap of what we've done so far. Because they're pretty different concepts to the pure things. And I'm just coming in, throwing in various different ideas at you. And you might be a bit shocked. So, recap of what we've done so far. I'm not really that happy with my artistic work. I think this evening I'm going to do some self-study art lessons just to get that even slicker. That side, I've got the key points across, and the key points are two balls suspended across this kind of pulley thing here. It's like a little rig with a rope. You're going to let them go, and B is going to fall down. The question we're being asked is, well, how do they move? And really all we care about is, what's the acceleration? Well, B's tied to A, so they're both going to accelerate the same. That's one thing to mention. And the way we're going to get at it is write an equation for both of them. For A, 4 forces, we wrote them out, arrows. We're only worrying about the left and right motion at the moment. All right, sometimes you will have to care about the up and down ones, but here it's going to be moving left and right, so we'll call right positive, and we'll say T minus the negative, and that's the friction, by the way. We were told it's 12.7, so that's the same as this thing, equals mass times acceleration. It's just Newton's law. You'll use it 239 times in the course of your mechanics in A level. So there it is for A. T minus Fr equals mass times acceleration. Do the same thing for B. This time your T is going to be negative. Watch out for that. Do watch out for that, because I know you're going to sit there just really, really keen to make T positive again. But since, just showing you again the arrows, I don't want to circle them and make it more messy, but you know, you've got to, the more you do it, the more you get used to the fact that the tension's going, kind of, the two arrows are going towards each other on the rope. So, and therefore, since we've called the clockwise direction positive, that tension will be negative. So there you go, weight minus tension equals 1.5A. The weight is mg. G is gravitational constant, 9.8, says in this question. And so we've got the two equations. Then we've got to use them to find B. Let's move on. So, well, you may or may not be surprised to hear that your GCSE days were all worthwhile as simultaneous equations. So, yeah, let me just do this quickly, and then I'll answer the question about T being negative. I'll say it one more time as clearly as I can, because it's a good point. So, simultaneous equations, there's the first one from A, and there's the second one from B. I'm going to just add them together. So it looks like if I add them together, I would get on the left-hand side 2, and on the right-hand side 4A. So that means that A equals a half. Now that was probably too quick for your average chipmunk, but, well, no, I'm not going to say too much more about it. Just convince yourself, look at that. If you add the left-hand sides, you get T minus T, and you'll get 14.7 minus 12.7. So you just, the T's go, and you're left with 2 on the left-hand side. Right-hand side, 2.5 plus 1.5 is 4. 2 equals 4A, divide them, A equals a half. Simultaneous equations 101. You could also get T if you wanted, by the way. You could also find the tension in the rope. We're not being asked to do that today. Don't do extra work unless you need to, haven't you? Okay. So yeah, say something quickly about T being negative. It's not really that it's going down. It's in mechanics, and this isn't just for the forces one. It's forces question I've chosen here, but applies for suvat, for any kind of kinematics moving. You'll have to choose a direction to be positive. So that's what this little weird symbol that I put in here is. It's supposed to be kind of a line with 2 arrows. I don't know, did I create that notation? Is that a real notation? I'm not sure. Make up your own. Come up with your own one if you want. Be delighted to see it, but you need to choose one direction to be positive. Once you've done that, all your forces in that direction, you're going to call them positive. So here it's going to be that T and the W. And everything going the other way, you're going to call it negative. So the ones going the other way are this T and that FR. That's the story. So when you see them manifesting itself, you know, here's that negative FR, here's that negative T, and then there's the positive ones there. So there you go, that's a good point. It's about choosing a direction. You could have done it the other way. If you'd done it the other way, believe you me, it would have still worked. All right, you can still come out with an equation if you choose the other side negative. It's just, yeah, your answers will then be negative and you'll have to interpret it based on the situation. So that's a little weird, little quirky thing. Okay, what have we got? We've got our two equations of motion. We've got our acceleration equals a half. We're more than halfway there. We just need to then do some more stuff about once the balls are released, what happens. Possibly do it in a new bit of paper. Although it might be good to keep that. Let's keep that picture alive and do it on a new bit of paper. So C, because we're going to let go of these. Oh, where am I? And B is going to fall to the floor. And the question here is, how long does it take for B to hit the floor? What we're going to use, Ooh. Spoiler alert, it's a Suvat. So I'm putting it down. And I'm going to fill in what I know. And we'll kick on from there. 1 meter. That's the distance that thing falls. The initial speed, 0. So the thing starts at 0. That's part of the question. I mean, if we read that, yeah, and in fact, if you do actually get your binoculars out / magnifying glass, the system is released from rest, just to really emphasize it. The initial velocity of this guy, this bad boy, is 0. Final velocity, now we don't know that. Now I could go off on a huge rant about that. Maybe not rant, but, you know, it's a bit of a weird thing. If I drop a pen, it's going to be 0 eventually, the final velocity. Okay, I would totally agree with you. If you drop something, it's going to stop moving eventually. But when you talk about final velocity, you're talking about just before it hits the ground. Because if I jumped out of the Empire State Building, my velocity would not be 0 as I hit the ground. It would be quite a bit more than that. So that's something that people find a little bit confusing. You think, well, something's hit the ground, so the final velocity must be 0. We're trying to think just before it hits. Anyway, huge distraction because we don't even need it for the question. What we probably do need is, if I can go back to my trusty acceleration equals a half, let's call it 0.5, just for decimalization joy, then we've got our A. Time, well, that's what we're looking for. Okay, so what can we do with that? Quick assessment of the situation. We've got S, U, A, and T. This looks to me like an S equals UT plus a half AT squared type situation. Looks more like a 7 than a T. I have remedied that now. Plugging it in, 1 equals 0 plus a half 0.5 T squared. Yeah. Well, 0 is kind of irrelevant. Times everything by 2. 2 equals a half t squared. So actually it's times everything by 2 again. Actually ends up 4 equals t squared. And you got that. So yeah. It's always through that, right? You know, I was going to think of saying something else, but if something's moving and it's a constant acceleration, it's going to be Suvat. You're going to write down your Suvat, you're going to fill in the stuff that you know. So the distance it fell down was 1. The initial velocity was 0 because it was released from rest. The final velocity, we don't know that. We could work it out. We don't know it yet. But luckily, part B had come along earlier and given us acceleration. So we had that. Time we didn't know. We scanned through all the possible Suvat equations, which we've known, loved, engraved on ourselves. Well, we probably just checked our inner left arm tattoos of them that we've had put on. And we chose the one that worked. And that's a bit of an art. I mean, I just maybe made it look easy, or maybe not made it look easy, but I just jumped in with it. It's a bit of an art. And the more you do, the more you'll be able to choose the right one. S equals ut plus a half at squared. That was good because we just needed t. We had everything else. We had a, we had u, and s. Plugged it in, got t is 2. So that's good. D, I might not even actually write it. Let's just read what it's saying. Suggest 2 improvements that could be made in the model. Well, look, applied maths guys, we're going to actually have to use like English language words to give answers. I know. I don't want any letters of complaints or anything like that. Well, if you do, send it to my secretary and we'll put it in the filing cabinet that's called the shredder. But words are required. So I guess you sometimes get this in pure as well, but in stats and mechanics in particular, they do like this. So I can't help it. I've got to just bang on a little bit. I'll do it quickly though. First thing is, and did it say it here? Usually it says the balls are modelled as particles. Yeah. Last paragraph. Balls are modelled as particles. So one thing you could say is we were just pretending that the balls are one point, a particle, but really they're a bit kind of wider. So you might want to do that. You might need to take that into account with the dimension. That's saying it falls 1 meter to the ground. The ball, in reality, the ball's got a thickness, so it might not be a meter. I don't know. That's something you could say. What else could you say? Something you could say. Gravity. Right. We've said G is 9.8. You could say that actually it could be more accurate than that. 9.81. Just an idea. I mean, I think you could get away with 5 or 6 different things for this. It's 2 marks, and as long as it's something sensible. But that's a good couple. One is point particles. You could try and change the distances to take into account the fact they're actually balls. You could say G could be more accurate, 9.81. Something that's going to come up more when you get into year 13, so the second year of A level, is the friction force. This guy. So at the moment, it was just modelled as being 12.7 flat, no questions asked. But I guess the more complicated questions that we get into, you could start saying that's variable, or it's modelled in some other way, or maybe as it gets closer to the pulley, the resistance changes, or some kind of more complicated sort of resistive force equation. That's something else you could say. So, yeah, I think that's a good few things. Balls are point particles. Might want to change the distances. G could be more accurate, and we can model the resistive forces differently. I'm sure there's other things you could say, but that's a nice 3. Okay, I think we got the job done. It's just a little introduction to mechanics. It looks long, the question, but actually it was hopefully a little bit less painless than it might have been. The concepts are a bit weird. The concepts are a bit different to pure. I get that. The more, though, I'd say the key part of it, and the reason I like this question is you've got a nice solid introduction to this F equals ma work, which is going to crop up a lot in mechanics. It's going to crop up in inclined planes. Oh, where am I doing it? Where you've got something rolling up and down a slope. It's going to crop up in any. Actually, sometimes there's a train with a carriage behind it that's pulling it along. Crops up in that as well. So if you can, even if you take one thing away from what we're doing so far as a foundation of this, it's get used to using F equals ma. Get used to, on the left-hand side, putting all your arrows there, your different forces, and on the right-hand side, it's ma. And once you've written them out, you can start manipulating them. Here it was simultaneous equations. It could be other stuff. Okay, going to go just now. Thanks very much, guys, and keep in touch. I'll be back tomorrow, 5 p.m. Bye-bye.